Especially so far across the world from my home in New York. My plan is to give 4 lectures, and when people talk about writing a novel, they always say, write about what you know. So I thought I would use the workshop to tell you some things which I think I know. But in the first lecture, I want to convince you that that spectral sequences are natural things to construct, and show you how to construct them in general. And then in the second lecture, my plan is to show you a very simple example, but show you that in fact, using this simple example, you end up with very subtle results. And the third lecture, I would also like to show you that the algebra of these ideas leads to connections in other parts of algebra, some of which then lead to ways to make computations. And in the last lecture, I want to talk about some recent work I've been doing with a collaborator in Serbia, in which we are applying some of these ideas in combinatorial questions, which is a little bit unexpected, but which I think is also a little bit natural. So let me start with the yoga for this, which is quite simply that mathematical objects are often filtered. So I need to tell you what I mean by filtered. Of course, the examples that I have in mind are, for example, if X is a CW complex, then I can think of X as a collection. I should use different notation here, I think, of skeleta. And so I begin with a bunch of points. I add some lines between the points. I add some disks. I add some balls. And in this way, the CW complex has a natural filtration associated to it by way of that you construct it. If G is a group, then there are many filtrations of a group. I would think that the most well-known one would be the lower central series, or various versions of the lower central series that you obtain. If you take a ring, then of course you can look at the powers of an ideal in that ring, and in each case, what we're assigning to the elements in the ring is a certain natural number about how deep it is in the object. So does something in here come from the third skeleton? Does something in here come from the nth derived part? Does something here come from some power of the ideal? So this is, in some sense, the most basic place in which spectral sequences arise. That is, as soon as you have information that you're looking to obtain from the lower skeleta, for example, you would like to know how does that information give you some information about the whole space. And so a spectral sequence is a way in which you put information together. So let me take the CW complex case as sort of a canonical case, and let's develop things from there. So for each k, we have the following short exact sequence of chain complexes and of course this leads to a long exact sequence in homology groups, but so we have hn of xk reduced by hn k plus 1, and then we have the relative groups. And then the idea that I want to use to construct spectral sequences is the following. I want to take this construction which gives rise to this long exact sequence, and turn it into a triangle. So let me start here with the homology of the 0 skeleton, which maps into the homology of the first skeleton to the higher skeleton running along here. And here, I guess, and here I'll put the homology of the pair. And all the way along here, I'm making little triangles like this. And the way that I've arranged them, I've put the asterisk there to indicate that I'm changing potentially all of the indices. Notice that in this triangle, if I go 2 maps, then that gives 0. And in fact, all of these triangles are exact. And so, so we can talk about exact triangles. And so let me organize this a little more generally, and let's just talk about something that looks like this, where these are modules, and I have a mapping I, a mapping J, and here I guess a kind of boundary mapping. And let's assume that this is exact, namely that, of course, the kernel of J is the image of I, that the kernel of the partial map is the image of J, and the kernel of I is the image of that. And I'm assuming that, actually I'm not assuming anything about D and E, except that potentially these are modules. They may be graded modules. They may be modules with 2 gradings. All of these things are things that will allow me to talk about them further. Now here's the beauty of this and formulation. Notice that if I take and apply the mapping J, delta, to elements in E, they land in D. But elements in D, I can apply the mapping J to. And so this gives me a mapping D, which goes from E to E. And the beauty of this is that if I take the composite of this map with itself, since when composed in this direction, I'm going by J and then by D, then I get 0, and so this is 0. And so we can then talk about the homology of E with respect to this new differential D, and I'm going to denote this by E prime. So given this triangle, this exact triangle of modules and morphisms, I obtain a differential on the object E, and that differential has a homology which I'll denote by E prime. So the reason that this construction is relevant is that, in fact, it can be repeated. And so let me define the following. Let's let D prime be equal to the image under I of D contained in D. And so if I take D prime, certainly if I restrict I to it, it will continue to map DI, D prime. And let me now define the following maps. These are tricky, but let me define them. Let me call I prime I restricted to I and D, and then I'll make here new maps like this. J prime of an element X will simply be J of X plus the boundary of E. In order to see that this is meaningful, let me just see here. Let's see. So, oh, I'm sorry. This is J prime. Yes, this is J prime of I of X will be J of X plus D of E. So here I must take something which is in the image of I, and then I apply J to it. And if Ix equaled Iy, then of course X minus Y would be in the kernel of I, which is the image of delta. And so I could write J minus X equals, X minus Y equals delta of Z. And when I apply J to this, I get J of D of Z, which is D of Z. So this shows that whatever representative I choose of I of X, I always get the same answer. And so this is a well-defined mapping. The mapping delta prime of E of a coset like this, it turns out, suffices simply to take the value of that, and you get a, this also is well defined by chasing around. And so the upshot of this is the following theorem, which is that if this diagram is an exact couple, an exact triangle, then so is the derived version of it, where everything has a prime on it. Well, I won't go through the details of proving this for you because that's horrible, but it's fairly clear what one can do now, which is that once you have such a thing, you can iterate it. And so in particular, we have E together with D, which goes to the homology of E with respect to D, which is E prime together with its D prime, which then can go to H of E prime, D prime, which will be, say, E double prime with its double prime, and continue on forever. Now, the example which I cleverly just erased, let's think about the homology of the cellular bits here. In this case, the homology of the K plus first skeleton relative to the K skeleton is simply a collection of copies of the integers over the K plus 1 cells. So in particular, you can think of this as the free group on the cells. So I begin with combinatorial data, that is, count up the number of cells and look at the free groups that are generated by these, and those lie along this line of E's. And I then begin to do this operation in which I take these successive homologies, and then the question becomes, what do I end up with at the end? And so let me analyze a little bit further, and then we can see that, in fact, we get something associated to the space, which is the CW complex taken completely together. So let me introduce some notation. Since I'm taking successive homologies, we'll let E be the first of these, and then we'll let E prime will be the second, and then E prime of E prime is E3. And this, of course, will be H of E1 with respect to the first differential that's associated to this. This will be the homology of the second E2 with its differentials E2, et cetera, et cetera, et cetera. And now let me observe also that D and E may be bigraded. If you like, the filtration level determines the first part of the bigrading. So I would want to think of this as E with a K plus 1 attached to it. And then this will be the co-grading, as it were. So if this were Q, then I would have here Q minus k plus 1, 1. So I bigrade in such a way that I obtain two pieces of information which together determine a total degree. So these may be bigraded, and ij delta have bidegrees. And so if I do this, and this, for this I need to make sure that I don't put the real numbers down. I already have. Here, in the case that we're looking at, so mapping J has bidegree 0, 0. This has bidegree 1, minus 1. This has bidegree minus 1, 0, 0, 0. So notice then the differential here has bidegree minus 1, 0. And more generally, when you derive these things, you discover that the rth differential, which will go from some PQ, will go to P minus R, Q plus R minus 1. And you get that by doing a chase through things, just by counting things up. So this is the general scheme that we see in spectral sequences, and all of the usual spectral sequences that one encounters have this shape. This is generally referred to as the homological spectral sequence. If I rewrite the case of the CW complex, here I have EPQ is P minus 1. And of course, it's clear, since assuming that my CW complex is not some horrible thing, that this is determined by a bunch of P cells, and hence we get that EPQ is 0 for Q greater than 1, and it's equal to the sum of copies of Z over the P cells in for Q equal to 0. And let's see, this means that the only differential that makes any sense is the differential D1, which goes from E P minus 1, 0 to E P 0. Oh, I'm sorry, that's backward. It's very easy to make those kinds of mistakes. And when I take the homology of this, then I will get down to an E2, which would go from here to here, which is 0. And so this spectral sequence, when I begin to work with it, immediately stops working, because the information, well, essentially the information looks like this. It looks like a chain complex, and when you attempt to do the next computation, it goes up into a big vast collection of zeros, And of course, I'm computing homology if this will equal its kernel, and there is no image, so the next homology will equal to whatever's left and whatever's left. So the question remains, after I've done this computation, what's it related to? And so notice that all of the discussion that I've made so far has to do with the letter E. What happened to the D's? Okay, that's really what the important question to ask is. So let me tell you how this relates. So here's the theorem. Let's let ZR P star be equal to the pre-image under D of the image of I to the R minus 1 going here from dP minus R star to dP star. Okay, and this will be contained in EP star, and let BR P star be equal to J of the kernel of IR minus 1 going from dP star to dP plus R minus 1 star. It's also contained in EP star. Then, having set this up from the exact couple, I get that ER P star is isomorphic to Z P star R on the P star R, and E infinity, which I'll explain in a second, will be equal to the intersection of all the ZRs over R and mod out by the union of all of these. So the thing to notice, of course, is that I've chosen everything to come from the D's. And furthermore, as I move further and further back in the D's, I continue to take the same smaller and smaller pre-images, and so their intersection lives in the right place. E infinity is the eventual homology. So E2 was H of E1 with D1. E3 is H of E2 with D2, et cetera, et cetera, et cetera. H of En minus 1, Dn minus 1. If, and I put this condition out, if this eventually stabilizes, then that's what I mean by the eventual homology. If it does not stabilize, then what I mean by the eventual homology is very subtle and requires a great deal more than one can do in an hour in an introduction. But in the case, for example, that the bi-grading on D and E is always by positive integers, then you have a situation where everything lives in the first quadrant. If you think of this bi-graded module sitting here, eventually the differentials grow too long and leave the region to go into zeros, zeros, and zeros. And of course, that homology will be whatever was there to begin with, and it will stabilize. So those are the situations which are most classical and most common to see. And I write this not as an obvious thing, but that, and by calling attention to this eventual homology, that in fact there are issues that are there which are difficult to resolve. It's also the case, of course, that one has to prove that this is going to happen, and that takes some conditions as well. So, having said all that, I can bring the G's back. So here's another interesting theorem.
When it stabilizes at E2 time, does it have some special name for that? Or?
Well, if all of it stabilizes at
E2 page.
at some page, then we say it collapses.
But
Right.
no special word for collapsing at E2 page.
Well, no, that would be the
Simply.
special words. Yeah. Yeah. So if at any stage of this computation the particular differential vanishes and all subsequent differentials vanish, which is, of course, easy to have happen if, for example, all your information is here, right? Then you say that it collapses from that stage on. So, but it would be best if it collapsed at E2.
Right.
Because then you could stop working right after that. And once my niece asked me what is a spectral sequence, and I didn't want to give her 4 hours of lectures to tell her what it meant, but so I said, it's a book, and it's a book where you can open to the first page. And you would like to know what's on the last page, and but you have to turn the page. So to turn the page, of course, you have to take the homology with respect to a differential, and that will allow you to see the next page. But sometimes you can only turn this much of the page, and you can see maybe in a little bit in the corner. So, for example, if you're here, maybe D3 is already 0, and maybe you can learn something about the lower left-hand corner. There are many PhD theses which are based on the lower left-hand corner of a spectral sequence. Okay. But then, of course, once you get to the next page, you have to do everything that you can to turn that page. Sometimes the pages get easier to turn. Sometimes you can never turn the pages. Some spectral sequences, they only tell you what the last page is, and you need to figure out what the first page is. Those are very interesting. So that's, and of course, collapse means that when you get to that page, you can always turn the pages for the rest of the book. So you've gotten to the end of the book by the nth page. Okay, well, let me tell you this theorem. There is an exact sequence . 0 maps to dp star mod the kernel of I r plus I dp minus 1 star mapping into PR plus 1 P star mapping out to by induced mapping on to image I R intersect the kernel of I. Okay. So let's see if we can sort this out. For example, in this case here, so we've already gotten to E2 by taking the homology, and in our case, the homology was given by taking the boundary map and then following it by inclusion into the next lower free group on cells. And let's see. So here I am at E2, and I'm comparing this with dp, what would be dp0, which I guess is hp of xp. And if I look at the kernel of higher and higher mappings, then I'm going to get 0 for that, because once I've gotten enough cells on, it stabilizes in the pth degree, modulo what comes from the p minus first, which would be 0 because there are no p cells. And then likewise, when I analyze this, I'll end up with 0. And so the upshot is, from this exact sequence, we've computed that the E2 term of this spectral sequence, which is the homology of this mapping here, is in fact the homology that stabilizes up here of the cell complexes, and therefore it's the homology in the pth degree of X. Now, here I didn't really specify what I meant by this. I think now I can reveal that this was singular homology. And so here what I've proved is that the singular homology of a cell complex is in fact isomorphic to what you get by taking the free group on the cells, a finite collection, and then using this mapping here, which of course once you go in geometrically and determine by incidence numbers and the like, this is the cell differential. And so what I've shown is that the cellular homology, the homology based on these combinatorics, is isomorphic to the singular homology for a cell complex. And all that falls out of the machinery that is here as a simple example. So in fact, when you pass on to the eventual homology, then of course the answers that you're getting at E infinity here are determined by the D's. So the D's have re-entered the calculation as in fact the thing about which you are calculating, whereas the E's are potentially, which are coming from the filtration, are in fact potentially easier to calculate than the homology that you need. So that's generally how it works. So let me write down another example, which has a little more depth to it than the example of cellular theory, but for which is in fact related. So in this case, let's let this notation denote for us a fibration. So this will be a Serre fibration. By a Serre fibration, I mean that this has the homotopy lifting property for simplices. So, you know, a very weak notion of fibration, and the inverse image of the point of a base point is the fiber F. So here I want to assume that B is a CW complex, and so if I have that it's a CW complex, then I obtain a filtration. Let's let J S be equal to the inverse image under P of the S skeleton of B. Then, since, of course, everything in E maps down onto B in a Serre fibration, E now is filtered by this sequence of spaces given by inverse images. And so I can put these together then and obtain a sequence of D's, and here a sequence of relative homology groups, which are given by the inverse images over each of the skeleta. So now you need to think about what it means to think about this relative group. Essentially, I want to be thinking about the S+1 cells, which are, from a homotopy point of view, just a point, but over a contractible space, the fibration becomes a product. And so essentially what I'm doing here is assembling over each cell a product with the fiber. And so when I take this homology, I end up with the cellular complex over B with coefficients in the homology of the fiber, and this will be my E1. And then when I take and study the differential will turn out to be the cellular differential determined by B. And so E2 here in by degree PQ will be the pth homology of B with coefficients in qth homology of F. Now here, of course, I need to be a little more cautious in what I'm saying, because, in fact, when I write this, I don't necessarily mean a constant coefficient system. That is, it's possible for B to have a fundamental group which is acting, and the action of that fundamental group then, of course, we all know that the fundamental group acts on the fiber, and so that action has to be taken into account here, which means for me that I really like to think about simply connected spaces, because I don't really like to think about these actions being particularly difficult, and I don't like also having to look at an E2 term, first page, where I can't interpret what it is that I'm looking at. Notice, by the way, that this is already a step forward. I'm no longer talking about E1, but I'm talking about E2. And in this particular case, when the fundamental group is tamed, as it were, I get a very nice expression for the E2 page. And above, I'm taking inverse images under the fibration mapping of bigger and bigger cells. And so this eventually stabilizes for any given homological degree to the homology of E. And so we usually write that this spectral sequence converges to the homology of E. And this is this of course is the Serre spectral sequence. In a very technical sense, what I've written down is in fact the Serre spectral sequence. Since Leray was only really interested in spectral sequences in cohomology, Serre's great step forward in introducing the Serre spectral sequence was to introduce a spectral sequence for homology, for singular homology. And so this is a fantastic result. Notice, by the way, that this is a first quadrant spectral sequence. And so if B and F are finite CW complexes, then this spectral sequence will collapse at a finite stage. And that's simply because it will all occupy some rectangle like this. Furthermore, if we use field coefficients, okay, then the E2 term, in the case that the fundamental group is tamed, turns out to be even nicer still and can be expressed as a tensor product of the homology of F with the homology of B. So that's a very beautiful algebraic object to be dealing with from the beginning. Let me just notice for you that, in fact, when you're in a position like this, you can deduce some quick calculations. So here's a very simple example for a theorem. If B and F are finite CW complexes, I1 of B is 0 and K is a field, then I deduced that the Euler characteristic for E will be equal to the Euler characteristic of B times the Euler characteristic of F. So in fact, for fibrations, for example, in the cases that you would be most interested in, this would be when E, B, and F are all manifolds. You can deduce from the existence of the spectral sequence this equation. So let's see if we can make a proof of this. So let's let P x y.
But for this statement, do you need K to be field?
Yeah.
Well, the
Yeah.
characteristic doesn't matter.
That's right. So if I calculate it from fields,
So
this will be
drop this.
sufficient.
You may drop this condition that K is a field.
Oh, okay.
But this statement.
Oh, okay. Okay. Yeah. Yeah. That's true. Let's let this polynomial p of xy be collection over p and q of the dimension of e to pq over k of x to the p, y to the q. So this is a bigraded, what I would call a bigraded Poincare polynomial, or you can think of this as a a generating function for the dimensions of the E2 term. Since it's bigraded, we put it in two variables. And so the first thing to notice is since E2PQ can be written as this tensor product, then this will be equal to the sum of the dimensions over k of this times x to the p times sum of the dimension over k q of k to the q. And so in particular, if I calculate p minus 1 minus 1, then that puts the alternating sign here for these dimensions and the alternating sign here for these dimensions, and therefore I get the Euler characteristic of f times the Euler characteristic of b. Now, all I have to do now is relate this to the homology of
This
E.
side you have the pxy, or
I'm sorry?
the second equation pxy.
Here?
The polynomial.
Yeah. So I have now two polynomials.
Yeah, but this one has to be equal to pxy.
No, this one?
No.
This is
That's
just
the
a
homology group.
right.
And then here you have polynomial on this. So this, the second equation is equal to the polynomial pxy.
Right. Yeah. Okay, good. Yeah. Okay. So now all I have to do is relate this to the homology of E. And so let me do this by waving my hands. How does this work? First, the dimension of the homology. I left off a very important point. The important point is how does E infinity relate to H star E k? And so let me put it this way. Let's see. Here I'll put P plus Q. The homology of E with coefficients in K then is equal to some P plus Qth filtration of this group, this vector space, which contains lower and lower filtrations down to F0, and the quotient Fp plus Q mod Fp plus Q minus 1 determines here EP1, and then the next one EP2, on down forever. So in particular, oh, I guess this is EP0 infinity. Oh, I'm sorry, this is not right. This is EP plus Q0, and this is EP plus Q minus 1, 1. This is EP plus Q minus 2, 2, on down like that. There we go. That's correct. So in particular, if I take each of these vector spaces and I add up their dimensions, then that will assemble the dimension of the union, and that dimension will be the dimension of the homology of E in dimension P plus Q. So we get that the dimension of HP plus Q of E, okay, is the sum of the dimensions of E P plus Q minus K. K, where K is 0 up to P plus Q. Infinity. So, getting back to this situation, I know that I'm in a situation where I have a box, and so eventually the homology will stop. I'm also in a situation where I have an expression for the coming from the E2 term.
This E2 P plus Q0, that's just 0. This HP plus Q is equal to FP plus Q. Not taking quotient.
Oh, I'm sorry. Yeah. I'm forgetting which direction I need to go here.
Maybe the first one is...
Yeah, maybe this is...
That's the 0.
That's the 0 one. And that's the next one. Yep. It's hard to keep track of these things. So let's think about what happens when a differential destroys something, making a new homology. Essentially, what's happening is some generator produces an image, which means that it ceases to be in the kernel, and it puts something in the kernel which it removes. It does this on one dimension off. So something comes in which is canceled by the alternating sign that goes away. It's exactly the same argument that you use to go from cells to homology when you calculate the Euler characteristic from the homology. So if we extend that argument up to a bigraded situation, then that same argument that allows us to get the Euler characteristic from homology extends to this case. And so in fact then this is already the Euler characteristic of E, and hence I'm sorry, this is already the Euler characteristic of E, and hence we've calculated two different ways and get the same answer. So that's just an example of the manner in which the existence of a spectral sequence allows you to deduce things quickly that you might not otherwise be able to do directly. So I'm supposed to stop at 2.
Can you say the same thing for non-simple connectivity?
It's very, very difficult to say anything.
The result is
I'm sorry?
Still, you get to say, and the result is correct.
Oh,
Not simply
for non-simply connected, the Euler characteristic. Certainly not necessarily by this argument.
Yeah, but in general.
And I'm not even sure whether there's something else that enters in general, but yeah,
It's still not so clear to me.
no, it's not clear to me either. No, no. Okay.